So hello everybody, I'm today going to talk about the reinforcement learning and its connection with nonlinear control, and I will also study a case about the pendulum problem, which is very well known in both literatures, but recently reinforcement learning is also trying to handle control problems. But the main issue is that the techniques which we know for reinforcement learning currently are just for discrete spaces, while in nonlinear control, most of the problems we know are continuous. So I feel this is the outline of this report. I will first talk about the motivation of why I chose this topic and what are my interests in knowing the first of all nonlinear control, and then because I'm working on reinforcement learning, and then I will talk about some of the literature of the combination of the reinforcement learning and the nonlinear control. After that, I will just say what nonlinear control problems are aiming to do and the assumptions, and then I will talk about the reinforcement learning, and then at the end I will say, okay, so what are the common things in both aspects, and then we will talk about the results. So essentially, the question is why reinforcement learning is good, and then what makes it different from the control, because we already have some practical problems in the control. And both in reinforcement learning, recently I've started solving these problems, and also the nonlinear control will have some already well-established solutions to these problems, and what are the similarities and how RL is related to NC. So we also will explore the performance of the RL by adding some uncertainties at the end to the problem. But generally, before going through the report, we categorize the different methods of dealing with the systems in 4 cases regarding the nonlinear control and reinforcement learning. The first case is that if we know the system and the environment of the system, and we want to control such a system, already nonlinear control have done very quite well, and then so no issues there. But the issue comes up when there are some unknown things in the system, such as if there is some friction and we want to see how to handle the friction. Nonlinear control already has so much literature in there, and then there are observers and controllers and etc. The other thing is that the other problem is that controlling and estimating some of the states of the system that we already don't know. However, in this report, I don't think I can cover that, but just to know, there is another part of the reinforcement learning which aims at this, and I think in the frameworks like DynaQ you may hear about that. And then at the end is that what makes both the nonlinear control and reinforcement learning to work on the same page, and that is what I recently have seen, and that is about the safe reinforcement learning by applying some Lyapunov design functions. The thing is that reinforcement learning needs an agent to interact with the environment and explores, and while exploring it starts learning. So the issue in reality is that sometimes the space is not, exploring itself can be harmful to the device, so potentially it means that we need some safe reinforcement learning, and that's where people are using the Lyapunov design for safe reinforcement learning. So just as a contribution to the literature, there are 2 methods for constructing Lyapunov functions. One is we use simply the nonlinear control and we know the system, but the other is that recently people have started doing so by approximating some int with some neural nets. The other methods are also known in the literature. However, the main issue with the second category is that the Lyapunov function it may not be possible to prove that the Lyapunov function designed by these neural networks are real Lyapunov, so some Lyapunov function. And so let's start with the RL. So as I said, RL is about learning from some environment which we don't know about the environment generally. Therefore, there is an agent that interacts with the environment. This agent from the environment will receive some reward, and the task is to accumulate these rewards and designing an agent which can achieve the highest reward. So essentially, we are about it. The reinforcement learning is about to maximizing the reward. But the issue is that most of the algorithms currently existing in the literature with the reinforcement learning, they deal with the discrete state and discrete action, while in the control problems, the problems are continuous in the continuous space. So the action, which I say can be some like an input control to a system, or mostly we can think of it that way. So the other issue is that the previous methods, previously we needed to know the precise model of the environment, but with the advancement of the reinforcement learning, people have modeled it with the Monte Carlo methods, and then going through the RL procedure. So I will explain the RL algorithm, the main RL problem in a few minutes. So just to talk about the RL versus NC, or reinforcement versus nonlinear control. In the nonlinear control, we need the knowledge of the system, like the relations between the states. So simply state equations. But in the RL, one can assume that the state space and relations are not given. So essentially, it is going to be more about the probabilistic stuff on how an agent can get the rewards and interacts with the system. In the RL, the desired control problem is achieved based on the rewards. And if we assume that each time we try is called an episode, which I will explain later, the RL tends to find the control, find the optimum control by trial and error. So essentially, there are so many times that the agent will try until it finds the optimum control that it is desired to find. If the system is changed or some uncertainties are added, RL can get adapted to it by the online learning procedure it has. Yeah, that's the whole thing. So in here, what I'm going to talk about. So this is NC. You already know it. The nonlinear control. There's an state equation. There's an state equation which defines the space, the environment of the system, and we already have so much talked about it in the nonlinear control. It is very cool. But what the RL is saying is a bit different. RL assumes that there is an agent that interacts with the environment, and this interaction, the parameters that we need to know are kind of Markov decision process. In this Markov decision process, we have the states, which is exactly the states as we have in the nonlinear control, like the x1, x2, the degree of the. In some dynamic system, it can be some degree or some theta, or it can be some speed or whatsoever. The action is usually, we can say it is the action that the agent needs to take. But in an environment of in the nonlinear control, the actions can consist of the input that we are giving to the system. And then we have the P that is a transformation which maps S to A, which maps S and A when taken at a time to the other state, and then we have the rewards that are given at a state at a specific state and action. So I should say that rewards are usually defined by the user and the one who's programming the RL. So the reward function is defined as follows, which is the summation of all the incoming rewards in the consecutive steps of the agent interacting with the environment, or each step that agent takes an action and sees a new reward based on the action and the state that it has. So potentially we can define also the policy, which is based on the state and action. An agent can take an action based on the state that it has, and it is generally called the policy. The duty of the policy is to maximize all the discounted future rewards, which we can call it, which is expectation of R of t at S of t equal to S. Or it means that at the current time t, if the state is S, what is going to be the value of the rewards, expected value of the rewards from now on. So essentially, really what the RL or reinforcement learning is aiming to do is to maximize this V. So for a policy, there are two. We can further extend this equation using the known R of t and write it in a recursive way, which is going to be V of pi at the state S to be equal to expectation of pi R of t plus 1, which is the reward of the next state, plus some discount of the V of pi, which is coming from there. So essentially using equations 4 and 5, we can reach to equation 6. And then we have the Q function, which Q function at the same time takes a state and action, which are taken at time S of t. And it is from the probabilistic point of view just one step ahead of V, because in V we just know if we are at some state, what is going to be the reward that we will achieve. And in the Q it's just about that if we have S and A, what will happen in the future. So essentially we can say RL is really trying to maximize also Q. So to update to maximize the equation 7, this recursive function is written. It is known in the literature, so that when we want to optimize the parameters of the Q can be a matrix, so like a Gram-Schmidt matrix, which takes a state and action and gives the probability of the reward, or it can be deterministic, or it gives the deterministic value of reward that can be achieved in the future. And the update step, which is defined here, is using the alpha and the gamma, which is at the at the current state. We need to search and find the best action that maximizes the Q, and then we add it with the reward received and multiplied by alpha, so that to update Q of S. So essentially it means that we can put a neural network instead of Q. Q can be like a Gram-Schmidt matrix that just takes an action, a state and action, and you can, based on that, find the best action that gives the maximum reward. The issue currently is that most of the methods that are trying to tackle this problem are based on the continuous action space problems, are discrete action. So essentially, the part that I'm working on currently is to make to assume the state space is continuous, and the actions are no more discrete. Currently, there are several methods in the literature that consist of discretizing the whole space, like for each action to k different values, and if we have m different actions, so in general the combinations that will find this maximum problem here are m to power k. But we can, this is a part of my PhD that I'm working on, is to, instead of that, we just define and say at a state t we can take an action, and at a state t we have some action, and we just can increase that action by some finite value, which is delta A of j. And it more makes sense in the control problems, because we cannot suddenly jump from a small value of action or a small value of input to a very large one. And then there is d variable here, which can be just -1, 0, or 1. That just increases a. That now instead of finding maximum a, we just find maximum of d along each dimension, and that takes just 3m. And m is just the number of actions. Action is the space of the action. So just to re-mention, S in RL corresponds to exactly states in the nonlinear control, and actions here are corresponding to the input U in the nonlinear control problems. So let's look at the pendulum problem. This is the pendulum problem that in the framework of the GYM, which is for reinforcement learning used. I'm using the exact values. So I assume that I have a controller which is U equal to x of 1 minus pi, because just to physically explain what's the problem is that I assume that the pendulum is just horizontally on the downward, and then we want to push it all the way to the top of the to the vertically to the highest position. So this is just a simple control we can use as input, and then we also want to train our RL on that. In here we also have B as the friction. What we do is to put the B being equal to 0, and by putting B equal to 0, essentially it means that we have no friction, and what we will see with this input is that the pendulum will move and will go upward to the top position and oscillates around that position using this U function. But we want to see what will happen if we also add some friction to it without knowing knowing that there is a friction or not. We want to see how to handle this. In the nonlinear control, if we add this input control, what we will see is that the pendulum will move and go up, and then after some time it will converge to the position of pi, which is around 3 here, will go there. But if we add some friction there, like B equal to 0.7, it will very soon damp and it cannot go all the way to the top position. And then in the third figure, we just have added some friction compensator using the paper we had the paper we had in lab 4, which was from Yazdani. And then here we have the reinforcement learning, which we have a neural net, which is assumed to be the input U. The interesting thing is that when you run this RL, you sometimes see that it also takes some probabilistic actions, and you will see that the pendulum will go around until it goes to the desired position. If we add some friction to it, what I observed is that the pendulum starts hanging around until it goes up. I will show the animations of that so that it will become more visible. So the conclusion with these figures is that it seems like RL, even without knowing that there is some friction in the system, even though it was trained on the system without the friction, it is showing some tolerance to the friction. So for that, I want to show the so if we have no friction using the reinforcement learning algorithm, what it learns is like this. So right away it moves the pendulum from any random position to the up, and that circle around it is the amount of input which is giving to the system. However, the undesired thing is that it never goes to, what I have learned in practice is that it never goes to the top and exactly staying there, at least on the experiments I did. But there are more experiments in the literature about this. But that's not what I want to show. What I want to say is that the interesting part is that when we add some friction to it, we notice that even though it doesn't know that there is some friction added to the system, it will just swing around as much as it can until it pushes the pendulum up to all the way to the top position. So, and if we further increase the friction, what it happens, we will see that the reinforcement learning method is just trying by swinging the pendulum to see if it can get to the vertical position or not. So I also must mention that to train this neural net for applying in this problem, it takes like 2,500 almost episodes. Each episode consists of one time the neural net or the algorithm trying to push the pendulum up. But the issue is that in the reinforcement learning we have the exploitation versus exploration. Exploration starts with some random moves, and essentially at the beginning iterations we will see these random moves are happening there, and then as we move on we will see the exploration decreases and the exploitation is furthermore added to the algorithm, and we will see that there are more deterministic moves taken. I must mention that the vertical axis is the amount of rewards the algorithm is taking, and in the pendulum the amount of reward is negative of the amount of the force added, torque added to the system. So essentially it means that the algorithm is getting penalized as we use more force or input, as we add more input to the system. So the conclusion which I have is that it seems like the RL methods are kind of more tolerant toward adding this friction, but however we need to explore more, and we need to find compare it with also more competitive methods like by, I don't know, changing the input control and etc. But it seems that reinforcement learning learned how to push the pendulum all the way to the up, even if we add some friction to it without the knowledge of without the reinforcement learning knowing that there was no friction in training procedure, but in the test time there is friction added to the system. The drawback of the RL is that it takes so much time, and it has to do a lot of trial and errors. Essentially, in the practice, this can cause some. This may cause some harm to the agent or to the robots or anything that we are testing on. So that's something which has to be explored more. And the good thing about the RL is that it doesn't need the knowledge of the environment generally. However, in the examples that we are exploring currently in the reinforcement learning, the state equations are known, but we just assume that the algorithm doesn't know that. So we need that because we need simulation. So these are the list of the references that I used in this report. And thank you so much for your attention. Any questions?
Good. So let's open for just some short questions. So it looks like you kind of agree reinforcement learning is kind of black box, while nonlinear control is white box.
So the thing is exactly that. I mean, the nonlinear control is really engineering. We need to know what is going on. We need to know every step of the things that we take. But in the reinforcement learning, we have a black box which is called neural net, and it is going to do whatever we want to do. But the issue is that we have to input a lot of samples to it so that it learns what's going on. And these inputs can consist of some reward, which still the reward is given by us. And also we assume that the environment is not known, because in all the simulations we know the state at least the control problems that people are currently solving in the reinforcement learning, the state equations are known.
What if they are partially known? How you can embed those knowledge into the reinforcement learning?
So, good question. The thing is, I wanted to explore that in this report, but due to lack of time, I couldn't do that. The thing is, they add another output to the neural nets or whatever model they are using, and beside whatever action is the neural net currently is predicting for some state, they will also try to predict the next state. Like, if you take this action, how much your pendulum or how much your carriage is going to move, and it's like that. You just train everything together in parallel because we have the computational power to do so.
Mm-hmm. Yeah. I'm okay with Q learning is slow. With a lot of computing. Today these are not disadvantages. So,
yeah.
So we want to see what real benefits we can get.
Well, current reinforcement learning was more successful in like games. I don't know if you have heard of these Atari games and these stuff.
Do you need to worry about you did lots of reinforcement, but you didn't converge to a behavior that you expected?
Yes.
There's a bias. Say for example, your parents keep giving you a candy, then you motivate you to a lot of things. Then you grew up as an adult with some strange behavior.
Yes, that's true.
So I need a candy to calm down, right? So that kind of bias, not really converging to, it converges, improves,
So
but didn't really go to the real optima?
The question of convergence in the, especially since we are using the neural nets.
I'm even
So-
challenging that reinforcement learning. They didn't introduce the concept of sympathetic stability.
Well, that's true, and that's one of the things I
You
really
don't
like
have to go to the
understand.
origin. Make sure when you write up your midterm, you have essay you need to write. There are lots of concepts. Then I hope you double check the Q learning literature.
Yeah.
Do they really care about that kind of a sympathetic
So there's-
AS notion?
yeah, sure. So I will add it to the essay. The thing is also, the issue is that when we use neural net in this update format that we have here, the neural net itself is used to find the maximum of Q, and also then based on the maximum that neural net itself has found, it's going to update itself. So essentially it means maybe we don't converge, and that's one of the issues with the using neural nets in the reinforcement learning. While there are other methods which they have some convergence guarantees, like when we use the Markov in the, well, I currently don't remember it, but there are other methods that have guarantees. But the issue with the guarantees is that they have like to search the whole space.
Mm-hmm.
So the convergence is, and even the stability of the algorithms is one of, not the system, the algorithm is one of the issues. And using the control notion of stability to make sure that the reinforcement learning will search some space, which is in this, like in the region of attraction. There are some papers about it. Is currently one of the hot topics in this field.
So you consider yourself as a computer scientist?
I consider myself as electrical engineering who has moved to computer science, and I want to know more.
And I really hope from your perspective that how nonlinear control can really help.
In what sense you mean?
In your machine learning endeavor.
So the thing is, these reinforcement learning algorithms are so much unstable. When we search in some space, when we explore in some space, the issue is that we may not find the optimum or the goal we want to. So what I'm thinking of is that maybe by taking help from nonlinear control or optimal control, we can somehow stabilize these algorithms and these methods in the future.
Well, any question here? Question you want to ask?
Another one I have is sort of just more for curiosity is why it tries to like push the pendulum down instead of just going up the other way. Like, you know what I mean? So when the pendulum, when you start your new condition, it tries to push it, and then it pushes it the other way, and it pushes, but it doesn't, and then it'll eventually stop.
Yeah.
But I'm curious if maybe that has to do with like the input energy is less than trying to
So
like.
the thing
force
is,
it
there
up.
is a maximum.
Towards that.
Yes.
Yeah.
Yes, there is a maximum to the torque, and that's why probably
You
it's
cannot,
not there.
Otherwise, you wouldn't need to do that, right? It's using the inertia.
Yeah, so it seems like. I mean,
Because when I was running that, the circles around it, you would see that it would go at most to a maximum amount, and it cannot go beyond that.
interesting.
Well, thank you very much.
Thank you so much.